Have you ever stopped to wonder if everything you thought you knew about the fundamental fabric of reality might just be incomplete? I mean, we naturally picture space and time as this perfectly smooth, continuous sheet, right? Like a seamless backdrop where the whole drama of the universe plays out. But think about your TV screen for a second. From the couch, the picture looks flawlessly smooth. But if you walk up and press your nose right against the glass, you see the individual pixels. What if space itself is exactly like that? I want you to completely rethink your basic understanding of reality today. Picture spacetime not as a smooth, continuous rubber sheet, but as incredibly fine, pixelated chainmail made of interconnected quantum loops. Welcome to this explainer. Today, we're diving straight into one of the absolute most fascinating frontiers in all of modern physics, loop quantum gravity, or LQG. This is the leading attempt to finally decode the quantum structure of reality. And the beautiful thing about LQG is that it doesn't just ask how things behave in space and time. It asks what space and time actually are at their most fundamental microscopic level. So here is our roadmap. We'll be looking at the epic clash between relativity and quantum mechanics, discovering the literal atoms of space, and visualizing how they weave reality through spin networks. Then we'll compare LQG to string theory, see how this math solves cosmic glitches like black holes, and finally look at how we might actually test it. Okay, let's jump right into section 1, the clash of physics, general relativity versus quantum mechanics. Here is the biggest headache in theoretical physics today. Our current understanding of the universe basically relies on two incredibly successful yet entirely incompatible frameworks. On one side, you have Albert Einstein's general relativity. In this view, gravity isn't really a force, it's just the manifestation of space-time geometry. Space-time is smooth, it's continuous, and it is highly dynamic. Matter and geometry are locked in this beautiful dance, bending and shaping one another. But then, on the other side, we have quantum mechanics, which governs the subatomic world. Quantum mechanics is fundamentally discrete. Energy and fields come in distinct, chunky packets. But crucially, it operates on a fixed, non-dynamical background. It treats spacetime exactly like a rigid stage where particles perform their quantum acts. So what does this all mean? Well, when you look at extreme environments in our universe, like the dead center of a black hole or the literal instant of the Big Bang, you desperately need both theories. But when physicists try to combine them, the math literally breaks down into infinities. Einstein's smooth, bendable continuum fundamentally contradicts the discrete, rigid stage nature of quantum mechanics. Moving on to section 2, atoms of space and time, quantizing geometry. So how do we fix this massive glitch? Loop quantum gravity brilliantly takes the core lesson of relativity, which is that gravity is geometry, and just forces quantum rules onto it. But to really grasp this, we have to zoom way, way in, past cells, past atoms, past even subatomic particles, down to a scale of approximately 10 to the power of negative 35 meters. We call this the Planck length. To put that crazy number into perspective, a Planck length is to a typical atom what an atom is to the entire visible universe. It is mind-bogglingly small. In loop quantum gravity, the geometry of space itself is quantized right at this scale. Just like you can't have half of an electron, you simply cannot have a length shorter than the Planck length. Below this scale, the very concept of size becomes completely meaningless. So we're forced to conclude that space isn't infinitely divisible. It actually prefers an atomic structure. It has a minimum possible area and a minimum possible volume. Space literally comes in discrete, pixelated chunks. Which brings us to section 3, spin networks and foams, weaving reality. If space comes in these tiny chunks, how do they all fit together? What we're looking at now is called a spin network. This concept was actually proposed originally by Roger Penrose and then heavily adapted in loop quantum gravity. Notice the little black dots or nodes. Those are the actual quanta of volume. They represent those discrete chunks of space we were just talking about. The lines connecting them, the links, represent the quanta of area, basically the surfaces that separate the adjacent chunks of volume. And here is the absolute most crucial thing to remember. This network doesn't exist in space. This network is the space. The specific mathematical states of these intertwined networks give us the exact physical geometry of the universe down at the Planck scale. But, the universe isn't a frozen photograph. Things move. Gravitational waves ripple. So what happens when we introduce time? When a spin network evolves, when those nodes and links interact, merge, and split over time, it sweeps out a surface called a spin foam.
Think of it like this. If a spin network is a 3D snapshot of quantum space, a spin foam is the 4D history of how that space evolves. And this brilliantly illustrates a core tenet of the theory, relational time. In LQG, there's no master clock ticking away in the background of the universe. Time only emerges locally from the sequence of these quantum events happening relative to one another.
Section 4. Loop versus string theory. The rivalry. Now, you really can't talk about quantum gravity without mentioning the elephant in the room, string theory. Let's look at how they stack up. String theory is incredibly ambitious. It wants to be a truth theory of everything, unifying all fundamental forces and matter into one neat package. But to make the math actually work, string theory generally relies on a fixed background spacetime, unobserved particles, known as supersymmetry, and multiple extra hidden dimensions, which good luck finding those anytime soon. Loop quantum gravity, on the other hand, is a lot more laser-focused. Its goal is just to quantize gravity directly. It doesn't try to explain what matter is, it just explains the space that matter lives in. Crucially, it is background independent, meaning it does not assume a pre-existing stage. It works perfectly fine in our familiar 4 dimensions, and it doesn't need supersymmetry to function. They are really just two entirely different, fascinating ways to approach the deepest mysteries of physics. Moving to Section 5, Bounces and Black Holes, Eliminating Singularities. Let's zoom back out from the Planck scale to the cosmic scale for a minute. This is where LQG gets really wild, because this pixelated version of space elegantly fixes the biggest physical glitches in relativity, singularities. In classical physics, matter inside a black hole collapses into an infinitely dense point. But in LQG, because there's a minimum possible volume to space, there is a maximum possible density limit. Matter simply cannot be compressed infinitely. It hits a wall. Because of this, the Big Bang singularity is completely eliminated from the math. Instead, LQG predicts a big bounce, meaning a previous, contracting universe hit that maximum density limit and then rebounded out into the expanding universe we see today. No infinite point required. The same logic applies to rotating black holes. The matter collapsing inside them hits this quantum geometry limit and actually bounces via a process called momentary quantum tunneling, or MQT. Now here's the crazy part. Because intense gravity warps time so heavily, what is just a tiny fraction of a second for the collapsing matter inside looks like billions of years to us on the outside. So a black hole is effectively a frozen star, pausing a quantum bounce for eons. Section 6. Testing loop quantum gravity. Finding the evidence. Okay, so this all sounds like beautiful, mind-bending science fiction. But physics demands proof, right? How do we actually test these quantum claims in the observable universe? Well, finding evidence is notoriously difficult because the Planck scale is just so vanishingly small, but astrophysicists are coming up with incredibly clever methods. Right now, in the present, researchers are tracking gamma-ray bursts from billions of light years away. The theory is that if space is a discrete, bumpy web, high-energy light might actually propagate through it at slightly different speeds than low-energy light. Looking to the near future, the focus shifts to what we call extreme mass ratio in spirals, or EMRIs. This is where a smaller black hole orbits a supermassive one. The discrete nature of LQG actually causes a tiny quantum wobble around rotating black holes. Interestingly, as a black hole spins faster, this quantum correction shrinks. And looking further ahead, upcoming space-based gravitational wave detectors like LISA, Taiji, or Tianqin are going to be perfectly positioned to observe these EMRIs. Operating in the millihertz frequency band, they'll meticulously track these orbital dynamics, specifically hunting for tiny, accumulated deviations from standard physics. These deviations would be the telltale signs that the orbiting black hole is navigating through a fundamentally quantum spacetime. As we wrap up this explainer, I want to share this profound quote from the source material. It beautifully summarizes the greatest conceptual triumph of loop quantum gravity. In physics terms, this theory gives us a Hilbert space, which is a mathematical framework whose states, quote, have a clean interpretation as quantum states of the geometry. These do not live over a background, but themselves build up spacetime. This is a total paradigm shift. Spacetime isn't just a stage where the actors, the particles and forces, perform. The quanta of space, those tiny interconnected loops we talked about, are the stage. They are the background itself. It's a mathematically rigorous, fully realized quantum description of geometry. So, I want to leave you with this final thought to chew on. Later today, as you look around the room you're in, or maybe look up at the night sky,
consider that the very emptiness you see might not be empty at all. Could space and time themselves really be made of tiny, interacting quantum loops, fundamentally weaving together everything we know about reality? If loop quantum gravity is right, our universe is far more intricate, more granular, and profoundly more connected at its base level than we ever dared to imagine. Thanks so much for joining me on this deep dive into the true structure of space-time. Keep questioning everything and keep learning.